Okay, so good morning then. This is our last lecture before the spring break. And as you can see, if you look outside, it looks like spring is coming. Anyway, let me remind you that our previous lecture was largely dedicated to a precise formulation of the rules of diagrammatic calculations, including all the elements that you can read from diagrams, all the elements of the mathematical expressions that correspond to diagrams, with a focus of course here on the resulting diagrams, because that's the key to really derive expressions. We talked about rules that apply to products of diagrams in the standard form, products of diagrams in the normal ordered form. We talked about products of diagrams acting on the Fermi vacuum state. We talked about rules that apply to products of the diagrams bracketed by the Fermi vacuum state. In other words, the expectation value expressions. Okay, and then we had a few examples illustrating the usefulness of these rules. I guess we'll continue today. My focus today, I would like to start anyway, today with the discussion of the Hugenholtz diagrams and rules that apply to them. So let's have a section, Hugenholtz diagrams. We already mentioned them here and there in our previous classes. As you remember, Hugenholtz diagrams are used to represent many-body expressions where we use anti-symmetrized matrix elements. Okay? And we produce Hugenholtz vertices by essentially collapsing Goldstone vertices. So they are, those are vertices where you do not have simple vertices connected by some additional lines or symbols. We really have only vertices, and we have bunches of lines that go into them and then leave them. Okay, so if I have, say, a k-body operator, let's start with this, written in terms of anti-symmetrized matrix elements. So that's the numerical factor in front of the second quantized expression. So I'm summing here over P1 through Pk and Q1 through Qk. We have an anti-symmetrized matrix element, P1 through Pk, Q1 through Qk. And then we have the operator part, which can be written either in the standard form or in the normal product form, where you would form these x dagger x pairs. Okay. Then the diagram that represents this expression simply will be some sort of a vertex. I'm going to maybe draw it this way, and I will have simply a bunch of lines that come into it and leave it. Okay, without in this case any particular orientation, because the p's and the q's are not defined in terms of their particle Hall character. So we have, I'll make dots this way. So we have P1, Q1, Pk, Qk. So the P symbols correspond to the creation operators that are leaving the vertex. The Q's correspond to the manipulation operators that come into the vertex. And as you can see, this vertex is just essentially sort of one point from which all these lines originate. Okay, we're not. It's not like in the Goldstone case where you would have simple vertices bundled together. Okay, and we know the rules for Hugenholtz diagrams. Good morning. How are you?
I am surviving.
Very good. You're smiling, so that's not a bad way to survive.
It's Hugenholtz diagram.
That's right. That's the reason. Hugenholtz diagram. Thank you. Smile. Okay. Indeed, you will see why today. Anyway, coming back to our discussion, we know the rules for the weights already. Okay, weights are determined by simply looking at the equivalent Fermion lines. So, for example, in this case, it's a very simple case. If I want to know the weight of this diagram, I have to drop all the p's and q's and then look at the skeleton. And clearly, we see that there are p equivalent, there are k p equivalent lines that are leaving the diagram. There are k equivalent lines that come into it. So altogether, the topological factor here for this operator is k factorial squared. That's the total number of automorphisms, okay, obtained by permuting the P lines and the Q lines. So that means that the weight of this particular diagram or skeleton, okay, will be 1 over GR, which is 1 over K factorial square, and that's exactly the numerical factor that you see here, okay? And I'm going to use today, usually I believe, a symbol H at the weight, because I want to make sure that we don't get confused. That is, I want to make sure that we do distinguish between the weights of the Hugenholtz diagrams and the weights of the Goldstone diagram. So now, as already implied, there's this issue of the sign factor. If you really look at our fundamental theorem of the diagrammatic methodology, then in the sign factor determination, we need to know the number of internal whole lines. Okay, we can figure this from a Hugenholtz diagram. Okay, but we also need to know the number of loops. And Hugenholtz diagrams do not use the concept of a loop at all. Okay, because we're collapsing all the vertices. That means that we have an issue here. How are we going to calculate the sign? Okay, in the case of the Hugenholtz diagrammatics. Well, in order to determine the proper procedure, we need to realize that actually Goldstone and Hugenholtz diagrams are related. They are actually related because every Goldstone diagram certainly has its corresponding Hugenholtz equivalent by simply collapsing the vertices, and vice versa. Every Hugenholtz diagram may have 1 or more Goldstone diagrams associated with it by expanding these vertices back. Okay? So there is actually a mapping between them, which can organize our work. That is, there is a mapping which a mathematician would describe as the homomorphic mapping. Okay, I'll make it longer. Okay, there's a homomorphic mapping between Goldstone and Hugenholtz diagrams. That is, as I said, you can always draw the Hugenholtz diagram corresponding to a given Goldstone, and when you want to go back, every Hugenholtz diagram will have 1 or more Goldstone diagrams behind it. That's why I said homomorphism or homomorphic mapping, not isomorphic, because that's not a one-to-one correspondence usually. Sometimes, you have a one-to-one, because it so happens that your Hugenholtz diagram looks that way. Okay, but usually you should expect multiple Goldstone diagrams corresponding to a given Hugenholtz. Okay, and we're going to use this homomorphic mapping to come up with a proper procedure of determining the sign factors. But let's first talk about this homomorphic mapping. You can already, as I already implied, clearly we can expect that we'll be able to produce Hugenholtz diagrams by taking Goldstone diagrams and essentially collapsing these Goldstone vertices. And let's see 3 examples. So my first example, examples. Okay, my first example will be a calculation of the matrix element Phi, A, P, and Phi, J, D, which we, of course, have already seen many times. We know that there are 2 Goldstone diagrams in this case when you work it out. Okay, so I just try to sketch them here. Okay, we have a diagram that has 2 loops labeled by indices of the determinants here, A, I, and B, J. And then we have a diagram which has actually only 1 loop. Okay, something like this. A, I, B, J. Okay, so there are 2 Goldstone diagrams in this case. We actually already read them, so if you read it, this one, you can see we have the weight of each, in each case is 1, okay, because, well, one simple reason is that all indices are fixed, so really you can't do anything else than identity, and obviously we do not have equivalent elements that you can group in classes other than having here 2 loops each forming 1 class, and here having 1 big loop that forms its own class. Okay, so what we have here when you read it is A, outgoing line J, V times incoming line I, incoming line B. Okay, the sign is a plus because you have two loops and two eternal whole lines. Okay, of course, I don't have to worry about scalars associated with the leftmost and rightmost vertices because those are defined as 1. Okay, and in this case we get minus A, J, V. If I look at A leaving, then the corresponding incoming line is B. If I look at J leaving, the corresponding incoming line is I. And if you now combine this together, you end up with A, J, V, I, B, anti-symmetrized. Okay? So we have already, of course, we have already seen it before. Nothing new here. So clearly that just reminds us that Goldstone diagrams are useful. They can give you the right expression. Well, so let's now look at this homomorphic mapping. I'm going to now try to squeeze these vertices here and here. Okay? What do you get? Well, if you do this, you end up, in both cases actually, you end up with only one resulting diagram, which will look like this. Okay? So that's the Hugenholtz. Okay? You can see that it's obvious if I squeeze this, I end up with this picture, and if I squeeze this, I end up with the same picture. Well, that suggests that there is only one Hugenholtz diagram representing the entire calculation. Okay? Well, you can always verify that this is indeed true. This is not the way typically we produce Hugenholtz diagrams. I'm just showing the correspondence. Okay? You can do a verification process. Maybe I'll do it here. How would you verify that this is indeed the only Hugenholtz diagram you can have here? Well, you can start the whole calculation from Hugenholtz vertices, simply. Okay? What is that we need to start the calculation? We need 3 vertices representing operators EIA, dagger, VN, and EJB. The excitation vertex EJB in our notation. Okay? And let's have lines here, AI for the de-excitation vertex, BJ for the excitation vertex, and of course you have 4 lines at the end, and we need to bracket this with phi, meaning that you have to form all possible resulting diagrams with no external lines. Well, clearly you can see that since I cannot connect lines within the V, the only picture that emerges will be the one that you see there. Okay? So the only picture that you will produce is indeed the one we obtain by collapsing Goldstone vertices. Okay? And there is more to it. Actually, that picture contains much of the information about the final mathematical expressions. Let's make an attempt to read it as much as we can read it right now. Okay? If you look at this picture or the other one, okay? What is the weight? So the weight of this diagram, the Hugenholtz style weight, is obtained by looking at the equivalent fermion lines. But there are no equivalent fermion lines in this diagram at all. No pair of lines there are equivalent. Furthermore, indices are fixed, which means that the weight is 1. Okay? What about the scalar factor? Well, the scalar factor will be a product of 3 scalars. Well, let's try to read it. Okay? The same idea. Outgoing lines go into the ket, incoming lines go into the bra. So we end up with AJ, okay, V, and then, then I can read it as IB, okay, and I know it's a Hugenholtz vertex, so I have to use the symbol script A here for anti-symmetrization, okay, but I don't know the sign, because if you look at this picture once again, well, I could have read it in this way, AJ, and then BI, okay, I simply cannot decide which way to read it because the whole thing is collapsed. So all I can say right now is that I know the expression up to a sign, because if it was AJBI, that would be a different sign. Okay? So I don't know the sign. But now you can see it's not entirely useless. I already know most of the expression. I just don't know the sign. Nothing else seems to be missing. Well, let's have one more example in this category to sort of get used to this idea. So the other example will be also an expression which we have seen before. I always pick up those in this case, these examples, because of course we want to make sure that we are getting reproducing the old results. So imagine that I want to go back to this case where Vn is the two-body operator in the normal product form. C2 is the excitation operator that we discussed, the one that you often use in representing wave functions. And you know, again, what are the Goldstone diagrams in this case? Well, so you would have, there are two of them. We already worked on it. Okay. Let's make consistent two vertices. The vertex on the left is Vn, the one on the right is C2, and you have to close it with a phi. Okay, the first diagram has two loops. The second diagram has one loop. Okay, and all lines here are summation lines, but I can label them because they have a well-defined particle whole character. So we have here A, I, B, J, and here I'll use A, B, and let's say I here and J here. So I is the one that goes from the bottom here to the top, and J goes down. Okay. All these lines are summation lines, so maybe let's add that information to our blackboard. So they're free. We have to still sum them over. Okay, and when you start reading these two diagrams, of course you're going to obtain the correct expression. You know, the weight here, if you really look at the weight here, but now I'm going to emphasize it's the Goldstone weight. Goldstone weight is 1/2 because we have two equivalent loops. And the sign here, okay, there are two loops and two internal whole lines, so the sign is -1 to 2 plus 2, which is +1. And for this one, the weight, well, here maybe we have to slow down a little bit. What do you think the weight is? Yes. Okay, is this clear to everybody? There's one loop. So sometimes, you know, you may think, well, there's one loop, so what can I do about one loop? Well, this is one of these examples that we already had last time of the self-adjoint loop. That is, if you drop, imagine that you're looking at this picture without A, B, I, J. That is the skeleton, okay? And that skeleton, you can do two things with it. You can, of course, there's identity operation, but there's also an operation which converts line A into B and line J into I at the same time. So you're not breaking these lines, okay? You don't try to detach them from simple vertices, but you're performing an operation which is different than identity, okay? So since we have two operations, the topological factor is 2, which means that the weight is also 1/2. And the sign, that is of course easy to determine. We have one loop and two internal whole lines, so it's -1. So altogether, when we work this expression out, we end up with 1/2 sum over A, B, I, J, and then, you know, reading from this diagram, the scalar factors will be I, J, V, outgoing lines are I, J, incoming lines are A, B, so that's the matrix element of the V. For the C2, we end up with outgoing lines A, B, little c2, incoming lines I, J. Okay, so that's the expression corresponding to the first diagram. For the second diagram, you end up with a minus, the sign is minus there, 1/2 summation over A, B, I, J. If you look at the V contribution to the scalar, we have outgoing lines I, J, V. If you read it in this order, you have to watch the order of symbols. So you have I, J, then you have B, A. Those are the lines that go into I, J in this particular order. Okay, and then you have for the C2, we have A, B, C2, I, J. Okay, you can of course recombine these two and obtain 1/2 sum over A, B, I, J, A, B, V2, sorry, V, A, copying poorly now, I, J, V, A, B. You can see that there is I, J, V, A, B here, and there is I, J, V, B, A here with a negative sign in front, so that's an anti-symmetrized matrix element times A, B, C2, I, J. And that's the expression which we already discussed before. We did actually the week's theorem work on it as well. Okay, so we get the right expression. Now, going back to the mapping, with Hugenholtz? Well, let's squeeze these vertices. Let's collapse them. What happens? In the first case, you can clearly see, if I squeeze this, I'll have 4 lines added, and I'll squeeze this, I'll have 4 lines added. So I'll have 2 vertices. So if I look at the Hugenholtz case, okay, we will have a situation like this. We have 2 vertices connected with 4 lines. Okay? A, I, B, J, of course they are being summed over. Well, if you look at the second diagram, you're going to end up with the same result after squeeze. Nothing new. In other words, once again, there seems to be only one Hugenholtz diagram representing the entire calculation. Okay? Well, we obtained this diagram by squeezing Goldstone vertices, but I could obtain it, of course, directly. So let's have a verification step here. Verification would be simply derive this diagram directly from the Hugenholtz vertices. Okay? So what are the Hugenholtz vertices in this case? What do we need to do? We have to form an expression of this type. VNC2, okay, and bracketed it with the phi, meaning form all the resulting diagrams with no external lines. Okay? So let's see. So for Vn we have this sort of picture, right? 4 lines at a vertex. For C, and of course they are, they're not going in any particular direction. Of course there are 2 outgoing lines, 2 incoming, but they don't go in a particular direction because it's a generic operator. For the C2, well, that's a different style of an operator because it's an excitation operator, so all lines extend to the left. They are Y-dagger type lines. Okay? Okay, I'm not going to put labels right now because they're all free. So we know that when you connect 3 with 3, it's still a 3, okay? And you have to form, from these 2, that's Vn, that's C2, you have to form all resulting diagrams with no external lines. Well, clearly we know that there's not much room for maneuver here. Okay, you just end up with one picture, okay? It's going to look like this, which is exactly what we produced from the Goldstone diagrams by squeezing them, okay? And of course labels, I know what to put as labels now. Right? I don't have to do it in the beginning here because I know that the lines that go from right to left are particles. So that's A here and the B here. The lines that go from left to right are holes. So you're going to throw I and J. And we know that all these symbols have to be summed over. Okay? Okay. So that's just a proof that indeed there are no other Hugenholtz diagrams that could somehow magically emerge. And furthermore, again, as in the previous example, the Hugenholtz diagram seems to be containing much of the information about the final mathematical expression. Okay, so let's try to see. Okay, if you look at it, what is the weight? If you drop the symbols, you end up with 2 pairs of equivalent fermion lines. So we know that the weight here of this diagram, the Hugenholtz weight, that is 1/4. Okay, I'll start writing it. It's 1/4. Then I have a summation over A, B, I, J. And now I have to read matrix elements. Well, okay, let's read them in one particular way. Here I have I, J are outgoing, A, B are incoming. So I end up with I, J, V, A, B, but it's anti-symmetrized because that's a Hugenholtz vertex. And then C2 is also a Hugenholtz vertex. So you have A, B, I, J anti-symmetrized. Edit. Well, the only thing I don't really know exactly is the sign once again. Because, if you look at the, say, Leibniz vertex, I didn't have to read it the way I did. I read it as I, J, A, B. But because all lines, come here, well, I could read it as I, J, B, A. Okay? I cannot really tell the difference from this diagram. So by simply reading these indices in different orders, I introduce the sign factor, right? If I read it as IJBA, well, that's going to differ from what I wrote here, IJAB, by a sign. So once again, I don't know the sign, but the rest of the expression is fine. Okay? You can see that this is indeed
a C there instead of the.
Oh, yes, thank you very much. Thank you very much. Yeah, so you can see that we are getting everything about this expression except for the sign. And you can actually, these expressions don't look identical when you compare what we obtain from the Hugenholtz versus what we obtain here, but you can easily check that they are equivalent expressions. Let's just do it. So we also get used to it. So after a sign, I'm going to keep the plus minus in front. What we have is a summation over AB ij, ij v AB, say anti-symmetrized, times AB C2 ij minus AB C2 ji. Okay, so what I did now is I expanded the anti-symmetrized matrix element and represented it in terms of the corresponding non-symmetric matrix elements. If you continue, you get plus or minus 1 over 4. Okay, sum over AB ij, ij v AB times AB C2 ij, and then maybe I'll simply subtract 1 over 4 sum over AB ij, ij v AB, AB C2 ji. Okay, and obviously you can see that I can say replace j by I and I by j here. Okay, well, it means that you also have to do it. You also have to do it here. Okay, so after rewrite, this is going to be plus or minus 1 over 4 sum over AB ij, ij v AB times AB C2 ij minus 1 over 4 sum over AB ij. Okay, then you have ji v AB times AB C2 ij. Okay, and now of course you can see that by this relabeling, the C2 parts are identical. Okay, so I can write it back together. I get plus or minus 1 over 4 sum over AB ij. So you can see I can write this as a common term, but here we have a difference. There's ijab, and here we have jiab, which means that if I flip, say these two, well, I don't have to do this, but if I do, you end up here with ijba. Okay, so altogether this is going to be an anti-symmetrized matrix element, ijvab times ab c2 ij, which is exactly the expression we produced before. Okay, straight from the Hugenholtz diagram. Okay, except for the sign.
The weight's different.
Oh, sorry, no. Yeah. What did I do wrong?
Well, no, I guess I'm a little confused.
Well,
Between
okay.
weights 2 and 3,
You mean two?
yeah, going from
I
2.
started with from here.
Right, yeah, I see that.
Oh yes, yeah. So I missed. Yeah, yes. Okay, you're right.
Oh, okay.
That's the problem. Yeah, that's the problem. That's where the problem is. Okay.
Here we go. Okay.
So I guess here. Let's see. Right. Okay. Yeah. Absolutely correct. Thank you very much. Okay. So once again, so let's maybe walk through this once again. So okay, the second step is obvious, right? I'm just writing this, expanding the C2 into two parts of it. Then what I do here is I sort of split it into two parts. Okay. I'm relabeling I and J here. Okay. You can see that makes the C2 vertices looking identical. All right. But here I have now. After this relabeling, I have, maybe I'll leave this for a moment. We have JIAB, okay? And really what I wanted to do, what I did, which I didn't do, okay, we'll fix it now. I'll switch I and J only, okay? This is an anti-symmetrized matrix element. If you do that, you will change the sign from minus to plus, okay? So this switching will produce a plus here. Then you will add this together, and the factor will be plus minus 1/2, which is what we were going for. Is this clear now?
Yeah.
Okay, I'm sorry I made this silly mistake. Anyway, happens once. Shouldn't, but it does. All right, thank you very much. Okay, so you can see I'm getting the right expression. The expression that is equivalent to what we obtained before directly from the Goldstone diagrams. Okay, except for the sign once again. So we have to do something about this sign factor. Well, so let's now try to develop the proper rule about the sign factors in the Hugenholtz representation from this homomorphic mapping. The idea here is actually very straightforward. The idea is that what you do, you draw one Goldstone representative for each Hugenholtz that appears in your calculation. Okay? And then you read the sign factor from this single Goldstone representative that you draw for the corresponding Hugenholtz diagram. Okay? You don't draw all Goldstone diagrams, you don't have to do that. You just pick up one per each Hugenholtz and you get the sign out of it. So let me explain why this is the right procedure. Okay? So let's imagine that I have some sort of a diagram, okay, where I will look more carefully at one specific Hugenholtz vertex. So that's a Hugenholtz diagram, and I have among various vertices, somewhere in the middle I have, a Hugenholtz vertex. Let's have lines going this way. All right. I'm going to call them P1, PK, Q1, QK. You know, picture suggests that there may be particle lines here, but they're not necessary. Okay, they could be particles or moles. I don't know if they're even internal or external. Because I'm really not telling you what's here, and what's here. Okay, so let's imagine I have some very complicated diagram, and I'm just trying to look at one specific vertex at it, and it's a Hugenholtz diagram. Okay, so let's maybe emphasize that. Okay. So when I start reading it, what do? The first thing I do, I look at the skeleton. Okay, meaning let's imagine that these lines, P and these symbols P and Q are free. So maybe I'll also say that here. They don't have to be there, not then of course you're not summing over, but I will sum right now. Assume that you are summing them over. So you look at the skeleton. Okay, meaning that the diagram stripped of free summation labels, and you read weight from it. Okay, so the weight will be weight of the diagram R. Let's call this diagram R. Okay, and it's going to be a Hugenholtz weight. So that step is obvious. That's what you do. You just look at equivalent fermion lines. Then you start writing the expression. Okay, you will have a summation over various indices. I'm going to just write the ones that we see, P1 through Pk, and then Q1 through Qk. All right. Of course, we'll have a number of matrix elements. Okay, I'll just write the one we see. So I'm going to put dots, indicating things that I'm not looking at. The matrix element here from the diagram will be P1 through Pk. Let's call this operator, okay, little OK here. It's K body, okay, so that's fine. All right, Q1, Qk. And it's anti-symmetrized because that's a Hugenholtz diagram. And of course, there may be more matrix elements in this expression. Of course, I cannot tell the sign because if I look at this Hugenholtz vertex, I could have read it in a different way. I could read, say, P's in the same order, but I could have read the Q indices in some permuted way because the diagram doesn't tell me which way to read it. Okay, so all I know is that this is determined up to a sign. And that's, of course, our big question here. What's the sign? Of course, there will be also some operator parts, maybe. Okay, again, I'm not writing them. So let's now try to do the following. Let's at the same time look at one Goldstone representative of this, of the diagram we are now analyzing. Okay? How can I, because of the mapping, that we already discussed, we know that I can get a Goldstone diagram back, by expanding these vertices. Okay, so let's just perform one of the maybe many expansions. Produce a Goldstone representative. Okay, so I'll draw it like this. You expand it, so you make sort of an oval shape maybe from it, or something like this, and then your picture will look like that. Again, I'm not suggesting that those are particle lines, I just expanded it, so I have to draw them in this way. I'll put labels P1 through PK, Q1 through QK, okay? And we all, of course, agree that this would be one of the, perhaps many, Goldstone diagrams that corresponds to this picture. So maybe I'll also write this here. It's a Goldstone representative. Well, we know how to read Goldstone diagrams completely, including the sign. So if I want to read this one, okay, let's see. I know that there will be a matrix element in it. I'll just focus on the matrix element now. P1 through PK, okay, Q1 through QK, the non-symmetric matrix element, okay. Of course, there may be more stuff. I'm not going to look at that now, all right. And the sign at this matrix element will be determined from the loops and internal whole lines here. Okay, so the sign will be -1 to the loops, the number of loops in this Goldstone representative, plus the number of internal whole lines. Okay, so those are, this is the number of loops, and this is the number of internal whole lines. Okay, in this diagram that I can determine. So and now let's go back to our Hugenholtz. Okay, well, if you really look at this expression once again, let me continue. So this equals plus or minus the weight read from the Hugenholtz diagram, okay, or skeleton. There is going to be a summation over all the p's and all the q's. So here I'm just repeating what I had. Okay, then we'll have some other parts of the expression we're not paying attention to. And let's start writing the symmetrized matrix element explicitly. What it really is. Remember, it's a linear combination of non-symmetric matrix elements corresponding to various permutations of, for example, Q symbols. So I'm going to open the bracket, and I'm going to start what's in it. So the first term is, say, P1, P2, I don't know, I write 3 of them, P3, PK, OK, Q1, Q2, Q3, and then QK. The next term will be, well, fermions Q1 and Q2. It will come with a minus. So you will have P1, P2, P3, dots, PK, OK, and then Q1, and then, as I said, Q2, Q1, I'm permuting Q1, Q2, and then Q3 through QK, okay? And then, of course, there will be more terms, K factorial terms, to be specific, corresponding to this anti-symmetrized matrix elements, and then, some dots afterwards, okay? Well, that's a very useful expression to look at, because when you look at it, you can see that the sign at this matrix element, okay, is really the sign read from a Goldstone. Okay, you can see if I look at this Goldstone representative that I just obtained by expanding the vertex, okay, all right. If, you can read it as follows. You can say that the sign at this matrix element is -1 to the L plus H read from this Goldstone. But it so happens that this is exactly the sign at this expression, at the leading term. Okay? In other words, you can say that the sign at the entire expression, that you don't know yet, is really this sign at this term. But the sign at this term, you can read from this Goldstone. Okay? So by picking up one Goldstone, you know what the sign is. Okay, you just read that sign from the Goldstone, and then you read, when you look at this Goldstone, you don't read this matrix element the way we used to. You stick an A at it, because that, you know that that's one of the terms in the corresponding Hugenholtz. Okay, so that's a very simple trick. Draw the Hugenholtz diagram, expand it, and then you know very well that the sign of the entire expression is the sign that you can pick up from this Goldstone. Because the leading terms in both expressions are the same. Okay? We call these Goldstone representatives Brandow diagrams. Okay? So this representative is going to be called from now on a Brandow diagram. And that is because Brandow was the one who came up with the idea. Okay? So we're going to celebrate this thing in this way. Alright? Okay, so essentially right now we're going to have a procedure which should work very well. Namely, let me clean this a little bit. Namely, a procedure that looks that works as follows. Okay, maybe I'll write it in points so we'll remember it. Okay, so for the Hugenholtz diagrammatics, right? Okay, how do we proceed here? You start by draw Hugenholtz diagrams and determine Hugenholtz weights from them. We know how to do it. We determine Hugenholtz weights by examining equivalent Fermion lines. Okay? We already talked about this. Then the second step that you take is represent each resulting Hugenholtz diagram, okay, by one of its Goldstone representatives. Okay, which we call the Brandow diagram now. Okay, and then in point 3 we assign Hugenholtz scalar factors, which means anti-symmetrized matrix elements or their products. Okay, so we assign Hugenholtz scalar factors, anti-symmetrized matrix elements, to each Brandow diagram. So as I said already, what you do, you look at the Brandow, you read the matrix elements, but you stick the A symbol at each one of them because they really are Hugenholtz vertices, just expanded back, to pick up all these other Goldstones that you don't want to draw. And then when you're done with it, your fourth step is determine the sign. Or the sign factors using, the Goldstone style formula. -1 to the LR plus HR, okay, where LR I'll actually label it with a B. LRB is the number of loops in the Brandow diagram, and HRB is the number of internal whole lines that you can also read from a Brandow diagram. Okay? Of course, you can read it from any other, but that's fine. That's what it is. All right? That's the procedure. And you see where it comes from. This procedure originates from this very simple observation. If I go back, just to make sure, that if I look at the Hugenholtz expression, of course I have anti-symmetrized matrix elements in it. But each of them can be expressed in terms of non-symmetric matrix elements, which are really the elements that define Goldstones. And if you look at it, if you pick up, say, the leading term, which I wrote here, okay, then the sign of the entire expression is the sign at this leading term, which you can read from a Goldstone by expanding the vertex accordingly. And that's all there is to it. Okay? So let's practice this procedure. I guess maybe after the break. Okay? What we'll do now, we'll practice this procedure, and we'll also learn one more very useful thing about Hugenholtz diagrams. Namely, you can use them as intermediate steps to derive all the Goldstone diagrams. Okay? So they are extremely useful. Okay? They are extremely useful in their own right through the procedure, four-point procedure that we have here. But they're also very useful as intermediate steps toward producing Goldstone diagrams if that's what you want. Okay? So we'll talk about it as well. Alright, so let's have a 5-minute break. I guess we'll start. And then we'll continue. In the meantime, if you have any questions, just let me know. Now, let's see, for the homeworks. You need to pick up your homework.
I don't think so.
Then I have it. Yeah, I think Josh also needs his. Okay. Remember about that. One thing I would like to actually ask you, I'll send an email about it, but maybe we can start talking about it. You know, we need to have a midterm exam. And you know, I was looking at the calendar, so I thought about something like April, I think it's 11th or something like this. Okay? You know, far enough in the material so that we have good questions to ask, right? And at the same time, close enough to the final so you can sort of treat it as a practice. Right? I guess trying to meet those requirements. Now, the question is, how would you like to write? in a way, I'd prefer to have it outside the lecture time, so you can have more time simply, because here we're a little bit constrained, and if I want to use this classroom, okay, because I'm not going to ask you to come here at 7 in the morning or something, because it's unfair, right? You can accommodate, but then
Unpopular.
Huh?
Unpopular.
Okay, yes, that's right, and yeah, it would be a little bit, yeah, I would do it if everybody's outvoted me, but I would say that would not be my first recommendation, okay? If you start at 8:30, that gives us 1 hour and a half. I prefer to have 2 hours, and I typically try to be a little bit flexible, that is, if someone needs extra 15 minutes or so, or half an hour, I'm really interested in seeing you solving these problems and, racing to the solutions, right? So, would you be okay if I tried to find a room, I don't know, sometime in the afternoon, or would you still prefer to use one of our lecture times? I'm new to this university, so please instruct me.
What week?
That would be, let's see, where's my phone? Phones have come, that's right. Mine's kind of an obsolete phone, but it still has a Okay. Yeah, so here, I'm thinking right now about 11 because it is Monday, so, it's sort of, because I can do it on Friday, if that's what you like on the game, so assuming that Monday is better because people but I'm talking about, say, in the afternoon, of course I would send an email and you would respond to me by telling what your limitations are, and I can propose a few days around that time, okay? So just to make sure, so we don't have any conflict with anybody, okay? But would you be okay with the idea that we do it outside the class? What we could do, if we do it on the day of the class, I could split that class like into, say, 1 hour would be maybe some material, and then, but of course it would not be on the exam, obviously. Exam would, the material for the exam would stop earlier, maybe a week earlier, right? So don't worry about me pushing it so to the minute, right? No way. But what I mean is, but we could also have a little review, maybe kind of last minute questions, right? Since we have enough time here to really do that, we could try, okay? But the question is whether you are okay with the idea of trying. Of course, that depends whether I can even find that room. I'll try. And that would be probably afternoonish.
I can assure you it's going to be a real pain.
Yes, okay, so I have to start working early on this, right? Okay.
You're a year late.
Yeah, we'll see, right? We'll see. There are not so many of us, so we don't really need some sort of super big rooms, right? So that's maybe one advantage in this case, right? But we'll see. If I fail, then announce the failure. And if we did it outside the classroom time, and then sort of, if we do it sort of like in the evening, then where maybe we can have a room which starts at some time and then goes forever. That is, nobody has to leave it because there's no class. Would that be okay with you? Right? Is everybody comfortable with this idea, or? Jared, you fine? Okay. Well, Nicole, you can also join us. We don't have to record it, okay? So don't worry, you don't have to.
Okay.
You're not going to record it. There's much to record, I guess. Okay, so let me try and search for it. I guess I'll talk to Rachel first and see what happens. We'll go from there, okay? We still have time, hopefully. So, really. Okay, so let me then restart. Okay, so what I want to do now is really, let's look at this procedure. So we will have now not some sort of a calculation where I don't know the sign or things are incomplete. No, I'll just now follow this procedure and we will see that we can get the entire expression, including the sign, straight from the Hugenholtz diagrammatic. Okay? Of course, the example will be, what we already did, that's, so that we know what to expect. I'll go back to this expression. Okay? One more time. Actually, I probably have one more example and then, to show what else you can do with Hugenholtz representation. But anyway, let's follow the points. So the first point says, draw the resulting Hugenholtz diagrams, okay, and determine the Hugenholtz weights. Well, we know what the resulting diagram is, so I'll skip that part. I'll just move right away to the diagram. Okay, so as you remember, we had a single diagram that looked like this. A, I, B, J, where A, B, I, J are free. Summation, that means summation indices. AD for particles, IJ for the holes. Well, the first point is determine, so I'm now following our procedure, determine the weight. weight is read from this diagram. So of course the first thing you do, you look at the skeleton, which will be something like this. That's all right. Oh, I just this one. Okay. There are two pairs of equivalent lines. So the weight of this diagram is 1/4. Okay. Then I proceed to point number 2, which says represent each resulting diagram. We only have one by its Goldstone representative. Okay. I'm going to expand these vertices to produce a diagram with the maximum number of loops. That's my advice actually to you how you do this. Because those are the easiest ones to evaluate. Okay, so I just expand it and produce one Goldstone representative. That's the Brandow diagram. So AI here, BJ here, and that's the Brandow. Okay, well then you go to point 3. You read the scalar factors. So maybe I'll write these points out. Try to put all of them on this blackboard. Point 3. Assign the Hugenholtz scalar factors to the Brandow. Yes?
I don't know if it matters, but when you expand it, how do you know it's a dotted line?
Oh, because that's a V. Okay, I know it's a V. I know what my...
You have to know where it came from.
Yes, yeah, of course, yes. So yes, exactly. So of course you have to be consistent. That is, you have to sort of yourself build the proper symbols, right, and then stick with them, right? So in other words, if there will be some other, maybe W operator, right, then you don't confuse D with the W. Yes, exactly, right. Of course I did, and we agreed a long time ago that the dotted line is the normal ordering, so I'm continuing on this. Very good. Okay, so what is the point 3 telling us? So you read this now, you don't look here really because you want to know the sign. So you look here and you read the scalar factor. So the scalar factor, dr, labeled by the internal lines. Okay, I'm just using our old-fashioned notation, but this has to be a scalar factor of the Brandow. So I'm going to put the B2 so that you remember that this is the scalar factor from the Brandow, not from the Goldstone, not from the Hugenholtz directly because we wouldn't know the sign. Okay, what is it? It's a product in this case of two matrix elements. So you look here, it is IJ, AB. So first you read it using the Goldstone ordering, but then you stick the A symbol. It's anti-symmetrized because it is really part of the Hugenholtz representation. And then you look at the second matrix element here. We have AB, IJ. Okay. And it's also anti-symmetrized. Okay, so we're reading from the Brandow, we're reading the Hugenholtz scalar factors. And then you proceed to point 4, which is determining the sign from the Brandow. Here. Okay, so my sign factor for the Brandow, which is -1 to the LRB plus HRB. Okay, and this is -1. There are 2 loops, 2 internal whole lines, so it's a plus. Now I've got all the elements that are required to build the final expression. The final expression is, so phi Vn C2 phi equals. It's the sign. So now I'm going to actually write this sort of schematic so that you will remember the protocol. Okay, sign read from a Brandow. Weight read from the Hugenholtz. And the scalar read from the Brandow, remembering that the Brandow scalar is really a product of anti-symmetrized matrix elements. Okay, so it's going to be D, in this case, the scalar factor with a B, meaning from the Brandow. So now if I execute this procedure, I end up with sign is a plus, weight is 1/4, okay, that's the Hugenholtz weight. Then we have a summation, our indices are A, B, I, J, and we end up with I, J, V, A, B, anti-symmetrized, times A, B, C2, I, J, anti-symmetrized. And that is the right expression, and the sign is correct in it. Okay? No ambiguity anymore. Now, of course, I don't know if this is a question that is tempting you, but what is the question that I want to now talk about is, well, what if I chose a different Brandow? You know, there is a homomorphic mapping, so Hugenholtz diagram typically has several Goldstone diagrams behind it. So in other words, the question is, can I choose poorly? Is it that I chose one specific Goldstone and I got the right result because I did so? Okay, well, it's not the situation in Indiana Jones where you can choose poorly. Here you can only choose wisely. No matter how you choose, it's going to be a good decision. And I'll show you this through this example. So what if I decided, okay, I'll go through this procedure once again. Okay, so I will start with point 1, which is the Hugenholtz weight. But what if I replaced the second step by choosing the other Goldstone that you can draw for the same situation, just by expanding differently? And you remember that other Goldstone was, again, 2 vertices, D and C2, but now expanded such that we produce this Goldstone diagram. Okay, you label it. Okay, I think I'm using I for the bottom. So the I is the line that goes from the bottom simple vertex to the top one here, and J is the one that goes down. Okay? So that's my Brandow map. Of course, it's a legitimate choice, because that's one of the Goldstones. Well, now we proceed to point 3. Okay? So I'm going to try to create a mirror image of this previous calculation. What do? You look at the scalar. It's a Brandow scalar, so you have to form a product of matrix elements, anti-symmetrized, and read from this diagram. So what do you get? We get, for the V, we get Ij, BA in that order. Okay? So your order really follows the rules of Goldstone reading. I, J, B, A, outgoing, outgoing, incoming, incoming, but you stick the A symbol in it because it's really a Hugenholtz representation. So it's an anti-symmetrized matrix element. Okay? And then for the C2 matrix element, you have A, B, I, J. Again, outgoing, outgoing, incoming, incoming. Okay? But once again, with an A symbol. So please remember, for these and for these, we're still following the same recipe. Outgoing lines, or maybe I'll use some color here, for the cat indices, okay? I'll still use the incoming lines. And so it looks like Goldstone, except for the A symbols. Okay? Because we are running a Hugenholtz representation, you have to use you have to add those script A symbols, right now at least, that's the notation we're using right now. Later maybe we'll switch it to something more compact. Okay? Those A's are because this is a Hugenholtz representation. It's really a Hugenholtz diagrammatics. Okay? So we have we're done with the scalar part, and now we go to the sign. Well, the sign is sign of the Brandow. It's going to be minus of this Brandow is minus 1 to the LRB plus HRB. And now you look, you have one loop and 2 internal whole lines. So it's minus 1 to the 1 loop plus 2 internal whole lines, which is minus 1. So the sign is minus this time. And let's now assemble the final expression from these pieces. Okay? The formula that you follow is the one shown here. Maybe I should also emphasize it. That's the formula in this case. Okay? Of course, you know, they were externalized with all sorts of operators, but we don't have them. Okay? So I read straight from these points 1 to 4 with the second choice of the Brandow. So what do I get? Phi, V, and C2 phi equals. The sign is minus. The weight is still 1 over 4. You're summing over A, B, I, J. And the matrix elements, read from the scalar, are ijv ba, okay, times, with an a symbol, times ab c2 ij, also with an a symbol. You can see that this is the same expression that we got before. They are, this expression and these expressions are exactly the same thing, because all you need to do is to bring this one to the other form, is to just flip B and A. Those are anti-symmetrized matrix elements. If you do that, you will change the sign from minus to plus, and you'll be back in the previous case. So you see there's no risk. You know, it's just that it will look different, but it's going to be the same mathematical expression. No risk there. All the choices you're going to make are good. All right? So don't worry about that at all. But now, I would like to go to one more step, because, you know, now we're trying to finalize our mathematics of diagrams. Hugenholtz diagrams are also extremely useful in producing Goldstone diagrams. Okay? So maybe we'll have a little section using Hugenholtz diagrams as intermediate or intermediate diagrams for constructing all Goldstone diagrams. Okay? This is another way of exploiting this homomorphic mapping. Okay? So we already determined that this homomorphic mapping allows us, through the trick of the Brandow diagrams, to determine the signs. This is when you want to stay within the Hugenholtz representation. This is when you are interested in deriving expressions in terms of anti-symmetrized matrix elements. And of course, many people do that. But what if you want Goldstone diagrams? Really. And I'll give you one reason. Spin adaptation is actually a good reason to do this. Okay? You can do spin adaptation with Hugenholtz diagrams. It's not easy anyway. Alright? So, we already know the procedure. Start with Goldstone component vertices and connect them. We did that. But you remember, it was kind of laborious, right? Wasn't it? Because, you know, you have to connect in various ways. You know, these Goldstone vertices have the simple vertices in them. So now you have to connect across in various complicated ways, and then you are, oh, there are some repetitions, do you recognize the repetitions? It looks like maybe it's not, it is a little bit risky anyway. If I deal with a problem like CCSDTQ, where you have 180 Hugenholtz diagrams and many more Goldstone diagrams, you may be a little bit afraid that you're going to miss one of them if you just if you start with Goldstone vertices and start connecting them. Okay, so there is a procedure that avoids this trouble, which works as follows. So let me talk about it now. And I would say that's going to be the highlight in terms of the practical knowledge, how to deal with diagrams. All of them, Hugenholtz, Goldstone, anything you like. All right? So the procedure works like this. Again, I'm going to try to write it actually because it's an important algorithm that we need to follow. Okay? So what you're going to do is this. Represent all operators by Hugenholtz vertices. Remember, we're heading toward Goldstone, but you actually start with Hugenholtz vertices. So you represent all component operators in our expression by Hugenholtz vertices, and we draw the corresponding resulting, so we call them here R, diagrams. Okay? Those are also Hugenholtz. So you start with Hugenholtz, you end up with Hugenholtz. Then in point 2, you expand each Hugenholtz vertex to produce all Goldstone diagrams okay. How to do it best? The best idea here is as follows. So I'll write like this. This can be done by drawing first one of the Goldstone diagrams and then by exchanging outgoing or incoming, but not both types, not both, so by exchanging outgoing or incoming lines at each Goldstone vertex. Okay? So in the second step, so in the first step, you simply first produce all Hugenholtz diagrams from the Hugenholtz vertices. In the second step, you pick up one Goldstone, just like you do Brandow. That's just, you start with one, and then you start exchanging lines at each Goldstone vertex to produce the remaining Goldstones. Okay? But in this, what is important is that you have to select which lines you want to exchange. Outgoing or incoming, but not both, because then you'll be really, multiplying your work unnecessarily, producing really many copies of the same diagram. Okay? Now, what I also want to emphasize is that we can help ourselves a bit in step one. Okay? We can actually simplify it by starting our calculation with the non-oriented Hugenholtz skeletons. Okay? So maybe I'll make a little remark here that step one can be simplified, I would say greatly simplified, quite often, by considering first non-oriented Hugenholtz vertices or non-oriented Hugenholtz diagrams, vertices. So in other words, you start with non-oriented Hugenholtz vertices, the ones that have no arrows, constructing non-oriented resulting, okay, I'll write this in place, R, resulting R by constructing non-oriented R skeletons, and by subsequently adding, I guess I have to stretch on this blackboard, or by inserting, maybe I should say, by inserting arrows in the resulting diagrams in all possible ways. Okay? It's a very systematic procedure which carries very little risk of making errors. And if you really practice enough, you can't make errors. So again, you start by representing each operator in your expression by Hugenholtz non-oriented vertex. You then draw the non-oriented resulting vertices, Hugenholtz style. Then and then here and then you throw arrows. Okay, which, as you will see, it's always very easy. Usually 1 or 2 lines determine the direction of the arrows. Okay? And then when you have the Hugenholtz, then you expand each Hugenholtz, and then you produce the, into the Goldstone form, and then you produce the remaining Goldstones by line exchanges. Okay, so let's practice this procedure. That's probably the last thing I can do today. Let's practice this procedure on the same example that we did. Phi, Vn, C2, Phi. So suppose I'm interested in knowing what are the Goldstone diagrams here. You remember, the previous procedure was you draw the Goldstone for the V, Goldstone for C2, and you start connecting. No, that's not a good idea. The good idea is to follow the procedure that I just described. So in my point 1, I start with non-oriented, remember I'm now using this extra hint. I start with non-oriented Hugenholtz vertices. Okay? So maybe I'll write it here. 1. Non-oriented Hugenholtz vertices. Okay, what are they? For the V, that's what it is. Just the V without arrows. And for the C2, it's going to be this. Okay, so this is V and this is C2. Okay, I just dropped the arrows. I don't want to be bothered right now with arrows. Well, then you go to the next step, which is for the resulting non-oriented Hugenholtz skeletons. Well, that's very easy. If you don't see arrows, you just connect lines. And we know that here we're talking about the expectation value. Okay, this is an expectation value situation. So I have to come up with the resulting diagrams with no external lines. There's only one possibility. 4 lines here have to be connected to 4 lines here. That's all. Right? Now, I throw arrows at this expression. Okay? So maybe I'll continue somewhere here. Well, there is not like we have many choices. Okay? So if I continue here, maybe I'll redraw this. Okay? The next step is insert arrows. We know that this is a 2-body vertex, that's a 2-body vertex. So each 2-body vertex is 2 lines that leave it and 2 lines that come in. So you have only one way to do it. Right? If I say I want to have 2 lines leaving this one, say this and this line, and 2 lines coming into it, I'm done with the diagram, right? So maybe I'll remove this and draw another picture so that you can register these steps. Okay, so as a result, I will end up with this form. Okay? And you will see when we do we'll be doing MVPT, there are not that many choices. Usually you pick up one line, throw an arrow at it, or 2 of them, and the rest of the arrows flow like a domino. Right? Because of this rule that at each vertex you have to have, say, the same number of incoming lines as the ones that are leaving. You just by counting this stuff, you produce it. But then we are saying, then we continue with the step 1. I want to have the final diagram. The final diagram should have indices. See, I don't have to have indices right at the start, unless they were fixed. If they were fixed, say this line was fixed, you would have to propagate that information through, because it's fixed. Or, if you don't want to do this, you can follow the procedure without any indices at all, even if they're fixed. But then you have to remember, where do you have to fix them? Yeah, then you say, but this line should be fixed because it's at the V. Okay, something like this. Very simple. Okay, so my final step here will be insert indices. See, now we're so now advanced in this that we know that this is a particle line, that's a whole line. So I know how to call them. I don't need to do this from the beginning. Okay, I can just do this right now. Okay, so this line will be A. This line will be I, this line will be B, this one will be J. Okay? And now I have my Hugenholtz diagram produced, right? But you can see in a different way than before. because I follow this procedure that involves non-oriented skeletons. And then when you have this, now you proceed to point 2. In point 2, we are supposed to start by drawing one Goldstone. Typically, we start with a Goldstone that has a maximum number of loops. Okay? So that it's sort of is the easiest one, I guess, to manipulate, but you start with. Okay? And then we proceed with line exchanges idea. As I said, you have to decide, before you do this, you have to decide which lines are you going to exchange. Outgoing or incoming. I will choose in this calculation, okay, outgoing lines. Okay, so I'll say that exchange outgoing lines. Okay? But I don't want to tell you that that's all you can do. No, if you decided a priori that you want to keep exchanging incoming lines, that's just equally good, okay? So it's your decision. It's really nothing else. You know, you will get the same final result anyway. So let me show you how these line exchanges work. So I start with this one. My second diagram will be obtained. Maybe I'll do it here. So you draw vertices. Actually, by the way, you can already predict how many exchanges you will have. You have 2 pairs of lines here, 2 pairs of lines here. So altogether, by exchanging these lines, you will end up with 4. Up to 4 Goldstone diagrams. You know it a priori. And that's a rule, actually. If you have n Hugenholtz vertices, that's 2 to the n. Right? If they are all together, for example, that's going to be 2 to the n, you know, Goldstone diagrams, possibly. Although some of them may turn out to be equivalent. Okay? So, you know, let's exchange. So I'm going to mark it now. So, okay, so this is Vn, this is C2, and let's say that this one has no exchanges, right? I didn't do anything. I just produced it. So here I will exchange lines at Vn, outgoing lines. So that means that if you look at lines at C2, I am not touching them. Outgoing lines at C2 are A and B. Okay? I'm not exchanging them, so I'm leaving them where they were. But for the I and J, which are outgoing for the B, okay, it's like you drag it. You drag it and you move it here. And so you drag this end of the I line and you put it here. Okay? That's the exchange of the lines now. Okay, so I ends up here. Then you take sorry, this is J, right? Okay, then you take this line, the beginning of the J line, and you drag it up and stick it here. That's the line exchange. Okay, and I got the second diagram. Then you continue. Okay, there will be 2 more cases, so how about if I prepare the way? Okay, in the next case you will exchange lines at C2. Again, outgoing lines, remember, that's what I'm doing. So I look at the beginning, the first picture, not that one. You always go back to the first one. Okay? If you look at C2, the outgoing lines are A and B. We'll be exchanging those. I, J are incoming, so I'm not going to touch them. So I'm going to start with drawing lines that I'm not changing. I and J. They are where they were. And now I simply pick up the A and drag it here without touching the end. Okay? So A will go this way. And then you take B, the origin of it, and you drag it and you dump it here. Okay? Now I'm done with that exchange. Okay? And finally, I will exchange at both. I also can do that, right? And you should always exploit all possibilities. So exchange lines at Vn and C2. So at both vertices that we have. Okay? Right? So you go back to this one once again. And you do this. So for the V, when, we exchange. We're going to put I down here. Okay? That's an I line. Then you're going to take J and put it up there. Okay? maybe this one. Sorry. So I, right, it's a line that goes from the bottom now up, and then J is here. But I'm not done, because I also have to exchange lines at C2. So now you take A and move it down, okay? So it will produce, okay, this I is overlapping, so let me make sure we see. Okay, so this is I line. Now I took the origin of A and moved it down here, okay? So that's gonna be now the A. And then I'll take the beginning of the B and move it up. Okay? Maybe I'll put this A here. Okay, and then it's gonna be a B. Okay? Maybe I'll emphasize these symbols. Can you see all this? I'll try and make it zoom in. Can everybody see it? So what we have is maybe I'll, no, yeah, I think maybe I should, you know, maybe I should. Should I redraw it or maybe I'll do it, okay? It's kind of smallish. So this is exchange at B N. Okay, so let's do it again, because this one is a little bit scrambled. Okay, once again, you take, you really have to be very systematic. You start with the V and you drag I down, okay? So you end up with this. And then you take J and move it up, okay? And then you take A and move it down. Maybe here. And then you take the D and move it up. Okay? Okay? So maybe then I'll erase this. Okay? So you have, as you can see, you end up with two loops. J, A, and I, B. Okay? Those are the four diagrams to reproduce. Now, of course, you look at them and there are repetitions. Okay? So diagram, the first one here and the last one are the same. Because you have to remember, all these lines are free. If they were not free, if one of them was fixed, well, I could have ended up actually with a new diagram where fixed indices got permuted. When indices are fixed, that could be a new diagram, although it looks similar. We'll have this in Kappa-Cluster theory, okay? That situation. We'll talk about it then. But if all indices are free, these two pictures are equivalent. Because, you know, I can just drop I, J, A, B. I know that I'm summing them over anyway. So, you know, all I need to do is to bring this one to the first, is just by rotating this vertex. I will simply unscramble these two loops. Of course, they will be using different symbols, but you're summing over these symbols anyway, so that's the same picture. And the same with diagrams 2 and 3. Okay? They're also equivalent. Because, again, if I want to bring this one to this form, I just have to flip these two indices. This will uncross lines A and B, like here, and it will recross lines I and J. They may not be called the same way, okay, but it doesn't matter because you still sum them over. Okay, so you can see, now I have a procedure that allows me to recreate Goldstone diagrams. The conclusion is that this and this, these are fine choices, okay? But you see, I did it differently. I didn't use the original Goldstone vertices at all. I started with non-oriented Hugenholtz skeletons, walked through it, and in the end I just exchanged lines, which is a very mechanical procedure. Okay, even if you have, you know, 5 different vertices, it's very easy to start exchanging lines as long as you sort of organize your work somehow. You know, exchange at 1, exchange at 2, exchange at 3, then exchange at 1 and 2, 1 and 3, and so on. We'll do this. Okay, this is very simple. So please remember about this procedure. That's the best procedure. Of course, this procedure has one advantage. It also allows you to stop earlier. If you are not interested in Goldstone diagrammatic, you stop right here. That's your Brandow. And you finish the calculation. If you want to see the Goldstones, that's how you get them. So you can see now, we have this nice mapping. Every Hugenholtz diagram can be actually then represented with Goldstone diagrams if this is what I want to see. Of course, you can ask the question, why would I ever want to see now Goldstone diagrams if I already know how to handle the sign factor in the Hugenholtz, right? After all, there are fewer Hugenholtz diagrams because of this homomorphic mapping. Okay? You can have sometimes, 4 Goldstones or more behind a given hole. So why draw Goldstone diagrams if there are so many of them? Well, there's one reason, and that's going to be our next class, right? Spin adaptation. There is a very neat procedure of how to integrate the diagrams over the spin variables. Okay, that is really simplify your calculations greatly. Diagrammatic. Okay, for this you need Goldstone diagrams. For this you need non-symmetric matrix elements algebraically, and for this you need Goldstone diagrams. All right. So this is going to be our beginning of our next lecture. It will take us a few minutes, and then we'll move on to Fowler's theorem and Hartree-Fock theory and all these other things we want to discuss after the break. Okay? Is this all clear? Great. Okay, so enjoy your spring break. That is good. So I'm sure you're gonna have a lot of fun, and I'll see you around.